Okay, so the clock just turned 15 minutes over 4, so let's get started. Okay, welcome everyone to the third installment, part 3 of binary exploitation course. So we have to go through this slide every time. I don't know if is there's anybody new, like do we have somebody who's here for the first time? You, okay, so this makes sense, great. So I'm Aleksander Mundjar. I am a third year computer science student here at University of Ljubljana. I am DragonSec SI team captain and a long time CTF player. I'm playing CTF for 3 years already. My interests lie in binary exploitation and memory corruption attacks, which means I'm solving CTF challenges and am dreaming of one day becoming a zero-day researcher, which is far away, but next to that there's system security and malware analysis. So this is a little bit about me. Okay, so last time we were talking about binary protections. So basically how smart people who figured out that attacks on software are very common figured out different ways to protect binary from memory corruption. We talked about different types of protections, so system-wide protections that concern every binary in the system, and also binary-specific protections which only work if programs are compiled to have them turned on. We also talked about return-oriented programming. This will carry a lot of weight for today because today we'll be talking about a technique that involves building a lot of ROP chains in order to gain control of a program that doesn't have any of the useful code already inside it. So for instance, libc functions system and such. We took a look at attack patterns. Red to win was our goal, which is basically a proof of concept technique where you have a basic stack smashing principle where you override the return address to redirect code execution somewhere else. Agenda for today. So first we will recap what we've talked about last time. So I think we'll be talking about, we'll cover return-oriented programming and protections. Then the notorious global offset table and procedure linkage table. I figured out while creating this presentation that I've managed to talk a little bit about these two tables in every presentation that I've had, but nowhere did I describe them very in depth. So we'll be doing that today. I have a lot of slides, not only one. We'll be talking about shared libraries. Specifically, we'll be spending a lot of time in libc, so what it is, how it works. And we will then build up to return to libc technique, which is basically a technique that improves return to win capabilities. Basically, when we don't have a win function that is given already by somebody who has written the program just for us to learn, we can still attack that software. We will finish things up with example from PicoCTF. PicoCTF is an annual competition for beginners in cybersecurity, and there were some tasks, some challenges that involve binary exploitation, so we'll take a look at those. And of course, demos after the coffee break. Okay, so protections. As I said before, we were talking about system-wide and binary-specific protections. Here we have listed ASLR, which is system-wide protection. It randomizes stack, heap, and shared libraries. What does that mean? The memory that is reserved or mapped for stack, heap, and for code that is inside shared libraries is randomized every time the program is being run. Then we have PI, which is position independent executable. This is already a case of binary specific protection. So we have to specify while compiling the binary if we don't want this protection enabled. What it does, it randomizes the ELF base. So now with combination So with combination of ASLR and pi, we have randomized the entire memory space of the program, so nothing can be reused. Every time you run the program, it has a completely new completely new area of virtual memory to use, and it shouldn't ever be the same, or it will be once in every 2 on the power of 84, I think, 48 or something like that. Canaries. So canaries are the feature of today's stacks. Basically, they prevent the stack exploitation. So when we have a stack frame, and at the bottom of the stack frame there is a return address, have a base pointer, and somewhere here is some array. Let's just say character A of, I don't know, 18 bytes. And here we have canary. This basically enables us to detect stack buffer overflows. Whenever we write or print or copy too much data into a pointer onto the stack, the data will eventually overflow and override the entire stack, including the canary. And there's a function, there's a check at the end of every function. So before returning, which checks for this canary to stay the same. So if the canary is the same at the beginning of the function and in the end, then it's okay. If the canary got changed during the execution of our function, something went wrong and the program aborts immediately. After canary, we have rel-row, which is relocation read-only. This has to do with the notorious global offset table. The global offset table is basically a cache for the program where the program stores addresses for linked functions, like functions from libraries, scanf, puts, printf, and so on. And if this table is writable for some reason, we can use that as an attack vector. We can overwrite pointers in that table, and if we overwrite, let's say, or corrupt a pointer that is written in an entry of global offset table, every time a function will be called, it will crash because the pointer will be invalid. The last one is the annex bit, which prevents us from placing shellcode on the stack and executing it. Annex bit says stack is not executable, so this whole area that is mapped for the program to use as its stack is mapped non-executable, and what cannot happen is we cannot point the instruction pointer on top of stack. This is what cannot happen. As soon as the program tries to execute some instructions that are placed on non-executable area in memory, the program will crash. We also talked about return-oriented programming. I will be drawing another one of these nice stack frames. When talking about return-oriented programming, we said that in order to be able to control program execution, so in this scenario, let's say that the canary I've talked about before does not exist, and we somehow gain the control of the return address, and we overwrite the return address with some arbitrary value. Then whenever this function finishes that created the stack frame, will return to that place in memory. If we can control that, we can redirect code execution whenever we want. But this is not really that strong, because after that the program will still crash. So we only have one jump. If we don't have some code already in the binary that we want to reuse, that is perfectly placed, then this does not help much. So we added something onto that, and we called it a ROP chain. So instead of just ending at the return address, we place a lot of addresses, G 6. We place a lot of addresses onto the stack, and these are called gadgets. So one of these guys points to some place in memory where valid instructions are. So for instance, poprdi ret. And this is a very important part. So every single one of these addresses has to point to a place in memory where there are some instructions, in this case poprdi, and eventually we have to hit the ret instruction, because after hitting the ret instruction we will return back to the next gadget, and so on. And in this way we can chain them together and make the program execute different parts of code separately. Okay. Are there any questions about this from last time? I went through this rather quickly. If somebody figured out some questions or has something to say about this, it makes sense, because it's very important. If this doesn't make sense, then everything we'll be talking about won't make a lot of sense. We also talked about ret to win attack pattern, where we had a program. Let's call it main that has a main function and also has a vdorne function and a win function. This is where the name comes from for the technique, return to win. Let's say that somewhere in the vdorne function we have a buffer overflow, and we are able to overwrite the return address. So we smash the stack, and we are able to override this return address. Oh, one more thing. Win is never called in the program. That's the whole point. So we have win, which is only declared and defined, but is never called. And the point is to call this win function. So that way we prove that we were able to override the return address and alter the execution flow of the program. Going back to here, we override this return address, which should point back to main, because main, that's not correct, like this. Okay. Let's call this prog, just not to confuse anyone. So the main program has a function main, which calls vdorne, and the win function is just declared. So inside the vdorne function, we override the return address, which should be pointing to main, because after the vdorne function is finished, execution should continue in main. But we change this by using our overflow, and we change it to point to win. So now, when the vdorne function will return, it will return to win rather to main, and that's how we've proven that we are able to control execution flow of the program. Sometimes also we are required to change the parameters of the function. Let's say that win is some type of function that we need to chain our exploit. Let's say it's a read call or a gets call, and we need to set the memory where we want to read or where we want to write. So for that, we use gadgets. We talked about them before. We use gadgets like poprdi return to set the parameters. Anything unclear about this? Still from the last time, still just recap. Okay. I already had this slide last time. It's exactly the same, but this time I have follow-up slides. So we will actually make sense of what GOT and PLT stand for and what do they do, what function do they play in the execution of our program. So it says here that these are resolution tables used to store addresses to dynamically resolve functions, printf, scanf, and so on. And yes, this is exactly what these tables are used for. if you want to imagine it differently, it's like caching. So every time a program wants to call a function that's not defined inside the program, it's defined somewhere in a library. Then it uses some resolution magic to get the address. But after the program gets that address, it can store it in a cache so that when the same function will be called again, eventually it won't have to resolve the address again. And these addresses are stored in the global offset table. And why are we interested in them? Because sometimes global offset table, so .got segment in ELF, is mapped as read and write. So not only can you read from it, but it's also writable. So we can change these entries. And usually how GOT and PLT work is that at the beginning of the program, the loader, don't quote me on this, I think it's loader, the loader knows exactly which functions that are not defined in our program will be used, and it already resolves the addresses and it places them inside the global offset table. This is how usually programs are run. And so we have two modes. We have actually three. We have the no rel row, partial rel row, or lazy binding, and then we have full. So no rel row and full rel row are the same in the sense that both of them have already filled out all of the pointers to functions. Let's say we have two functions. We have printf and we have gets. In here, these pointers are already pointing where they should be pointing. And it's the same for here. I won't be writing it down, but it's the same for here. What is interesting and why I have to be discussing this is this middle part, which is a lot more complicated. I don't know why it's even there, because these two make perfect sense to use every time, mostly. But this is the thing that it's sometimes used, and how it works is at the beginning. So when the program is being run at the start, so let's say the start, the entry point, this table, printf gets just point to procedure linkage table. Procedure linkage table is there to help resolve these addresses. So let's say that printf is being called at the beginning of the program. The first time it's being called, the program will look inside the global offset table. It will find that the address is not yet resolved, and so it will jump right back to the procedure linkage table, and the procedure linkage table will jump to a function that's called dlresolve that will resolve the address and then place it here. We'll say printf libc. And so we see the whole picture here. Basically, whenever we want to call some of the functions, we jump to plt scanf, for instance, and at the beginning, global offset table is pointing right back. It's pointing right back to the procedure linkage table, and there is some code that calls dl runtime resolve that internally resolves the address of scanf, and then I have this like that, and writes it in the global offset table. So every other instance of scanf that's being called is treated like from a cache. The address of libc is already stored there, and so it doesn't need to resolve again. And it's the same for printf. Whenever printf is called for the first time, global offset table will start pointing directly at the code, and there's no need for DL runtime resolve anymore. And this will eventually also... In demos, we'll have a look at the example where this is actually happening in the code. It will make more sense then, but are there any questions right now about this? This is also quite important for today. The return to libc technique uses both PLT and global offset tables in order to achieve the goal of calling systems. So if anything doesn't make sense, or if I've skipped some part that I shouldn't, let me know. This is just... Oh, can you guys see this? This is the question now. That's why I asked you to move. Can you see at least some of the addresses? I'll be showing this live after the coffee break. But basically what I wanted to show here is how complex and how this all looks inside the debugger. So we call scanf, and you can see that it says up there where the green arrow points, it says scanf at PLT, and there's an address that says 45F. So 45F0, and then I inspect what is on 45F0, and we can see that there's an unconditional jump to somewhere, and that's the unconditional jump from PLT to global offset table. And then if we take a look at where it jumps to an address that basically says 45F6, which is just PLT plus 6. And then there's another unconditional jump, just a little lower, that says 45C0. And if we look at what code is at 45C0, we see there are some pushes, and then another unconditional jump, which jumps to 5010, and there is a libc address, and this libc address resolves to DL runtime resolve. This is the binary that actually resolves, and after this is done, address here changes from a PLT address, oh, sorry, not, yes, address here changes from, so this would be this one, changes from 45F6, from this, changes to scanf. And the next time scanf is being called, all of this doesn't happen. It's just jump to here, and the address of scanf is already in there. This is the whole point. Okay, I hope it makes some sense as it is now, but we will look at exactly step by step how it happens in the demos, in the debugger and all of that. Okay, yes, yes.
So we kind of need to resolve the address of the function that we are calling, right?
Yes.
Because, I don't know, when the loader loads the program into the memory, it also loads the libraries that we need into a specific part of the memory. But we are not sure
Yes.
those
Exactly. We'll talk about exactly that now. But yes, okay. Do you have any other questions?
Just, if kind of we would kind of load them into a specific part of memory, then we won't need a resolver to kind of resolve their addresses, right?
Yeah, usually it's like that. It's here, in here. It makes sense to store those addresses that are being used, and the loader already knows which of the functions are not defined in the program itself. And so yes, it can resolve them while loading them in the memory, but not here. With lazy binding, it's not like that. And why am I talking about lazy binding? Because it happens a lot, and it's very confusing when it does. If you're used to this and that, which the only difference is that one is writable and the one is not. The one is right and the one is wrong. Another is wrong. So this one is right, which is not, which is full red row. It's not writable. This is good, and this is very bad. But in the sense of pointers and the loader, they are the same. But yeah, this happens a lot, and if you're not familiar, if you don't know that this is an option, that this can happen, it's very confusing when inside the debugger and you're trying to find out how that address got there, or in the worst case, why isn't it there yet? That's the worst part. Okay, so we'll talk a little bit about shared objects, just because libc, so the majestic word that I'm using everywhere, is a system library that's filled with functions like scanf, puts, and so on. You already know this. You maybe do not know how exactly shared objects work. Don't worry, I don't either. I'm still learning. But in essence, how it works is you have multiple programs, processes. Let's present them with some nice squares or whatever these are. And then this guy wants puts, this guy wants printf, and this guy wants scanf. And let's say that you've just booted the system. Nothing else happened. These processes are the first thing that's going to run on your process, on your, let's say it's Linux. There is, and this is RAM. The shared objects, in this case SO files, so libc, libm, and any other lib you like, are not here yet. But as soon as this program is ran, the loader sees that not all of the code that we will need while executing this process is in here, but it needs some of the code from the libraries. And so the library, in this case libc, is loaded in RAM on some physical address. And then, let's say this process then finishes, and the next one starts. And this, again, this one needs printf, but it's still in the same library. So when this process is loaded into memory, this stays exactly here, just the virtual address is different for every process. So every process that is using the library, because it's only code in there, it's not writing to the memory, it's only reading, it's only executing instructions. They can all use the same physical address, just they are all mapped to different virtual addresses. And that's how shared objects work in a very, very, very rough and short explanation. I don't know the depths of how virtual addresses are formed, why are they formed, when does this copy, when does it not. Don't ask me that, I'll be honest with you. But this is as much as I know. Okay, said everything we should here. So, why do we care about these shared objects? Why am I talking about them here? Well, because sometimes the programs that we want to exploit, so the code, is very short or small. Let's say there's only a few system calls and that's it. But as soon as that code is linked to a library that has hundreds of thousands of lines of code, then all of a sudden the attack vector for us widens just by using code from the library. And this is mostly why we care about it, because we want to use the code to exploit the binary. And that's where return to libc comes in. So it says here that we want to execute code that's not part of our target binary. We can use the shared libraries, and the return to libc technique does exactly that. Okay, some code. Not a lot of code, that's the point. Let's say that we have a program on your right. I hope you can all see the code. It should be big enough. The program is rather simple. The problem is rather obvious. There is some space reserved on the stack for the variable name. Then the gets function is called to read some data onto the pointer name, and it returns. That's all it does. And we've compiled it with these protections. So we see partial railrow, this one. We don't have canary, so this basically enables us to do anything. And we don't have pi, position independent executable, so we know exactly where main is and where all the gadgets are that are inside the elf binary. Yeah. But the question now is, can we spawn a shell here Or can we execute arbitrary code just from that? There is no win function here. This is the difference today. We don't have a win function that we can jump to just prove that we've redirected code execution. Here, there's nothing. But it is dynamically linked. So we do have libc. Are there any ideas? Just brainstorming. First, what do you think? Can we spawn a shell here? Exactly, it wouldn't be up on the slides if we couldn't. Okay, that's a great idea. But question, how do we know what to write there? ASLR is enabled, even though pi is not. It's not a position independent executable. The ASLR is still enabled on the system. So shared objects are randomized. So even if we were able to build a chain to write something in the global offset table, which yes, we have a function that writes stuff. So gets, we know its address because of the pi, and we can build a ROP chain that can do exactly that. Write some data whenever we want. That's.
We can probably figure out the address of some of these functions, right? And then we kind of look at relative of that address where the function is going to execute is located.
Great. So the idea is that if we get a hold of one address inside libc, then we can calculate relatively to that address, the address of, let's say, system. Let's say they want that function. The system function sounds quite promising for our cause. But how do we get the leak? How do we get a hold of that random address that you mentioned that we used? Yes, yes, I really like the way you're thinking. So what the colleague said is eventually, so if we take a look at if we consider the lazy binding relocation, eventually addresses of puts and gets will be inside global table, inside the global offset table. So we should be able to read them. Yes, of course, but that's the good part. But how do we read them without crashing the program? Because as soon as let's say you stop the execution of the program right at the end, then you see the global offset table, you see the addresses there, but then the program stops, it crashes or it returns.
Some address for the library, right? And the other one to kind of modify the return address and
yes, so we will have two ROP chains to do that, exactly. And the first one will be to first leak the libc. Do you have any idea how would you do that? So you cannot use just any function because all of the functions you have are these two. Everything else is in libc already. So you cannot use like functions like system or stuff like that because that's in libc, you don't know the addresses. But you can call puts because, or gets, because there's no pi. We know they are statically loaded. What does gets do? Puts, yes. We should use puts. How? So we already figured out that we should call puts at PLT. Great, because that we know the address of. But what will be the argument? So if we just call puts with nothing, it will just take whatever is in the RDI register and take that as an argument if it's a valid memory address or not. The address of the GOT table. Great. So should I just say GOT? Exactly. Yeah, you got it. You figured it out. We can use this. So the puts will just print itself out. It will print us the address of itself. I only use puts because it looks great. You could also use gets, of course. You could use gets.got here, or any other address that's in the elf memory space. I don't think there are any libc addresses other than these two. I'm not sure on that, but yes, you can use any memory that has a libc address and it will get printed out like that. Great. I'm very impressed. So what now? So let's say we built a chain for that. We build a ROP chain that looks something like this. So we have, I'll make this a little larger. So for this, we build a ROP chain. It looks something like this. The return address goes pop RDI. Then we have puts got, and then we have puts PLT. So this is roughly the chain. And when the function, the main function in that scenario finishes, it will pop got into RDI, and it will pop puts.got into RDI, and it will call puts at PLT. Great. And at this exact moment, after the puts finishes, of course, address will be printed onto standard out. But right after puts finishes, what's here? This is the next address the program will jump to. What's here? This is a stack. This is a stack. So main local vars. It's a main stack. We don't know. There could be something or there couldn't be anything useful. 99.999% of time there's nothing useful there, and it will just crash. And that's the problem right now. So we were able to leak the libc address, great, but then our program crashes. I can now move to the next slide because we already figured the things out for a nicer image. Like this. Yeah, I skipped a few slides because we talked it through and we already figured that stuff out.
One question.
Yes.
Why do you need to leak the library so it's in the memory, so it's different each time, right? Which means that if I know where the library is loaded, it doesn't help me have the next time that I'm trying to.
No, but this happens during the execution of the program. So the program itself, when the library is already loaded, you get during the execution, so when the library is already there, the program itself gets the address of the library. So you'll create a script practically that will get the memory.
Oh yeah, okay, never mind. Yeah.
And it will return it to your script or standard out, and you will take the okay.
So yeah, now that you guys got it, what should be here then? We control this whole area. We have a gets call. Yes, we will do that.
Sorry, from standard out actually.
Yes, we will read the address, but the program will still crash. We don't want it to crash. Yes, that's the next part. But we cannot do that in the same chain. Because when we put the chain on the stack, the program will execute it and give us a leak. At that point, we cannot change the chain anymore. We've already written the entire chain, and we don't yet know where the system call is or whatever you're referring, where the libc addresses are. Yes, we will read it from standard in, but what I'm asking is, what happens to the program then? Exactly. With what? Yeah, it's great thinking, but what do we need here? What is one? We need to keep the program alive. That's what we need to do. Exactly. Yes, we just write main here. And that's it. Now we have a leak. and the program will stop at the gets call, because it will call main again, and it will be halting there. It will be waiting for input, and that time we can use to read the address, calculate our offsets, build another ROP chain, and send it again. Just reuse the overflow. Okay, great. We have that on the slides as well. There we go. Okay. So now we're here. Just my drawings are not as pretty as this, I guess. So, okay, we have this. I spoiled it now, didn't I? Okay, yeah, I spoiled it a bit. But, so now we have a leak. You have the plan written already there, but try to still think with me. What's the plan now? Oh, I won't be deleting this. Down here it's main. Now we go back to main. Main, and somewhere here gets, and this is waiting. Now what? And during this time, we already calculated system is at something. We have this address now. Now what? Yeah, we already calculated the system address. What do we do with it? Why? We can just...
Can you just put it in the return address?
Yes, we can just reuse it. We have the primitive of smashing the stack, redirecting code execution. We can redirect the return address into system. Great. So we should do it. It should look like something like this. We have a stack frame. At the bottom, there was once return, but now it's system. System. Okay, and this is all gibberish. Great. What's the problem with that? What will happen now? So the main function will return, and it will jump to system. And what will happen in system? There's no arguments. So the system internally will just look at the EDI or RDI register, and it will say, "Oh, this is my argument," and it will use it. It doesn't care if it's valid or not. And what type of argument does system expect? A string. Yes. Yes. Great. So it should be. I don't know if it's a constant char or something, but yeah, it should be a string that represents a path on the system to a binary to be executed. Great. Now we just need that here. How do we do that? Yes, but you need a pointer to that, and that's on the stack. You don't know the stack address. Yes, we can. We can write, instead of gibberish here, we can say bin sh null. But the problem now, we need this. We need a pointer. We don't know the pointer to that on the stack. Stack is randomized. Okay, so now the big problem is we already figured out that we want to call system. We want it to execute some string. In this scenario, it's bin sh. But we don't have it anywhere written that we know the memory address of. Code with what? With system?
No. Aren't you running some code on the stack?
No, these are just gadgets. These are just addresses, just the ROP gadgets.
Okay. You are not able to run the code on the stack because it's memory, so it's not marked as executable.
Yeah, so basically stack is not executable. This is just return-oriented programming. We're just putting gadgets on stack, and with the gadgets we were able to leak the address. And now we jumped back to main, reuse the same vulnerability, and now we're trying to call a shell. x86 64, yes. Yes.
So you gotta leak the memory, the address of the buffer then somehow.
That would be one option. But if you don't know where the buffer is, can we create that buffer somewhere else? Just for fun.
Probably on a random stack address and hope it repeats something.
Yeah, we'll be here for a long time. In 32-bit, yes. In 64-bit, no. So down here, this is still stack. We still don't know the pointer. So we've now tried to write it on the stack, but what if we try to write it somewhere else? So there's no pi. So we have the whole elf. We know the addresses of every elf segment. Raw data, BSS, dynamic, everything. Why not just use one of them? Okay, great. But how are we going to do that? So for system, it's too early. How are we going to do that? Sure, you can call malloc, but calling malloc is a long way from writing binsh to it.
Yeah, sure.
But we have a function already in the binary that reads stuff. We have gets. Can we maybe use gets to write binsh somewhere? I don't think that's void. I think it's char, but bear with me. Gets expects a pointer, and it reads data. It reads a string onto that pointer, so onto that memory address. Can we use that somehow? Of course we can. Yeah, of course we can. So what do? It's very similar to this. Just switch out the parameters. This is an address to some instructions that are already in the binary. It basically function. Somewhere in the function it says pop RDI return. We just say start executing here, and then it pops a value from the stack, the next one on the stack, into the RDI, and returns to the next value.
Yeah, in order to pass an argument to the function, you need to load the registers with appropriate values before you pop it.
Exactly. This pops a value from the stack into the register.
But just the okay. Yeah.
And after this is done, we can call the function because the value will be already in the register. We basically control the whole execution because we control the whole stack. It's like stack machine. Okay. So here we again start with pop RDI. But what's here? This is, so now we're building a ROP chain that will write our binsh onto some address. Let's say that address is, I don't know, hex 418. Somewhere in BSS. BSS is like appropriate segment for that. There's nothing important there usually. So let's use that address. So what should we put in the RDI? Based on this signature. That address, exactly. Okay. Now what? What's the next thing? So now we've popped an address into RDI. Now all that's left, call gets. So now gets will call itself, and it will expect input, and it will write it to that address. So now we just write standard in, we say bin sh0, it will be written there. But after that, the program will still crash. So what do we need here? Main. Exactly. Cool. So now we have bin sh, we know the pointer to bin sh. We have a leak, so we know where system is. Now we need a final wrap chain to actually call system bin sh. Okay. Great. So we do this all again. We are back in main. So now we'll be calling system this. System, we know the address to. We calculated it from the first run. Bin sh, we know the address to because we've written it in the memory. So now we just have to piece things together. It's the same as here. So we start with pop. Okay. What's next? Exactly. What's here? System. Okay. And this will fork. It will spawn a child system with forks internally, so we don't need to care about this here. This will probably crash also. There's an instruction inside of system. I've got some critics for not showing you that the first time we were doing the red to win. Inside system, there's an instruction that's part of the x86 instruction set. It says it's move ABS. It's a very annoying instruction. Why is it annoying? Because in order to work, it needs stack pointer to be aligned to 16 bits. So at this point, stack pointer points to system when it gets executed. And because stack pointer, in this exact scenario, it would actually work because stack pointer would move down here and it will be okay. But if you write, sometimes you will write wrap chains that will leave a stack pointer pointing in this column, not here. And then inside system, this instruction will be called and the process will crash. That's why sometimes what is necessary is another empty ret instruction. It's very weird. What does a single ret instruction do? So basically, when I was talking about gadgets, when you have pop, RDI ret, we usually point it here. Well, when it comes to ret, we just point it here. And what happens is nothing. Just the stack pointer is reduced, so 8, or in 32-bit, 4 is added to the stack pointer. That's the only thing that happens. And why we do that? Because of the instruction that basically says, if stack pointer and FF isn't 0, I'm gonna cry. And so that's why we do that. Great. So we just did return to libc. Now I'm gonna tell you something else. We didn't need this. I just had some fun. We didn't need that. Because every libc has bin sh already in it. So here we could have said bin sh is something something and jump directly here, and here we would say bin sh that we calculated here. Basically every libc has a bin sh null byte string already inside. That's why it's always bin sh that's being called, never bin bash. And also because bin sh is 8 bytes, it's perfect. When the space is limited, not when you have gets and you can overwrite. But when the space is limited, 8 bytes is a lot better than 10 bytes. Okay, great. So we already did all this, all this, all this. Conclusion. We already know all this. Okay. Before we go to Pico, I only have 2 challenges. Both of them I was able to solve during the competition, but for one, I don't have a working exploit anymore, so we will just brainstorm that, how to solve it. It will be very, very, very similar to this. And there is another one that has a lot of code, and the vulnerability is not that easily recognizable, and it has all the protections. So every protection is enabled. We will see. That's usually how actual zero-day research or how actual bugs are found, not by this. This doesn't happen. This is just fun to do. Usually, researchers find stuff that we're going to see later. Okay. So we'll just brainstorm this quickly because we're already nearing the 1 hour mark. A few more minutes. Okay. So we have a binary here. I hope you all can see it. Nah. I'm so sorry. Basically, it's the same binary as this one. Exactly the same. The gets is being called. There is no canary. NX is disabled, so we can execute code on the stack. That is possible. Canary is found, although there's a thing here. Canary is found because this is a 32-bit binary. And 32-bit binaries do not have canaries. Never. This is a false flag. The first time I saw this, I was very confused, man. But yes, 32-bit binaries on x86, so basically x86 binaries do not have canaries. So basically what we have here is a simple gets. There's no canary. Pi is disabled. What can we do? Oh, and one more thing. It's a static binary. What that means is that every function that is being used, so get EID, set res EID, gets printf, it's already loaded inside the binary. There is no, it's not linked. We don't have libc. But the idea is very similar. So I will try to walk through this a little bit faster, but basically, I'll let you think for a while because I need to wipe this board. No, we have the great boards that can move, so I don't need to. Cool. Okay, now with all of that knowledge, what can we do there? Just pretend it's 64-bit for now. It's just the conventions are different. We'll work through that. Yes, you just solved the challenge. So, but this is the brute force way, because still you have to know the address of the stack. And because it's 32-bit, that's something like FF7 something 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 known value, known value, known value. 1, 2, 3, 4. This is all you have to brute force. This is 12 bits. It's not much. That's why, yes, on 32-bit system, nothing is safe. You can brute force most of the stuff. On 64-bit system, this wouldn't work because this here would be +4 or +6, and we can't do that. There's another way to do it. Of course, this is possible. What he's talking about is basically we do not even care about ROP chains or anything. We just write shellcode onto the stack and just choose an address that was once on the stack and just repeat executing that exploit. And in about 200 or 128, the stack will realign again, and we will get our code will be executed. But we will still want to do some ROP chains because that's why we're here today. Yeah, we can, but why? So the idea is the same. We still need binsh. Oh yeah, why are we doing binsh all the time? All of this, how this works is all of these programs are running on a server somewhere, and we are exploiting them over a network. And if the yes.
Couldn't we just leak the stack pointer and then can know? I mean,
How? Maybe. I haven't thought about it. Maybe, but I don't see how. Basically, if you want to leak, usually how you leak a stack pointer is by leaking the stack. So you basically have to have a pointer already on the stack. Let's say that a write function takes a parameter that's on the stack and then just writes too much data, so out of bound write. Then maybe on the stack there will be some actual stack address, and that's the only way how you can basically leak stack addresses. Leaking the stack is not very easy, usually. Very rarely does it become really apparent how to leak the stack. But here what we can do is basic ROP chains. We can use we have the gets and the printf. What we need is, what we want is system, yes. Because system executes binaries, or executes binaries. But what we actually want is a syscall that does that. System is just a wrapper. We can use execv, for example. This is a syscall that's internally being called inside system, which means that we don't necessarily need the whole function. We just need this. How are system calls being called in assembly? Does anyone know? How do you call a write syscall? Let's say that, what? Exactly. In fact, interrupt, oh shit. This is syscall in x86. So whenever this instruction is executed, whatever is so corresponding to the EAX register, the syscall will be called. So here is the ID. So sys_id. The ID of the system call is in the EAX. So if we say EAX and then interrupt 80, if you say EAX is, I don't know, 5 and then interrupt 80, system call on the 5th place will be called. I don't know which one it is. I think it's fork. I'm not sure. But we can control registers. I mean, we have gadgets. We have pop, EAX, ret. We have these gadgets. Usually we don't have these gadgets. Why do we have it now? It's because of the static binary that has a whole lot of other code in it, just because it's statically compiled. So there's no libraries. And the possibility of finding this gadget inside a statically compiled binary, even this small, is very likely. I almost don't believe that you cannot find this inside a statically compiled binary. Almost impossible. Unless somebody really tries. But the point here basically is to build a ROP chain that will call interrupt 80 with EAX pointing to 59. Believe me or not, I'm not sure, but I think that's the ID for execv. I'm not sure, so I'll just write here execv ID. That will be better. Okay. And then we call interrupt. Of course, execv is a system call that expects 3 arguments. it expects a pointer and then 3 more pointers, basically. It's 3 pointers. How do this? Path, then we have arg, and then we have end. It's something like that. Basically, path is what do we want to call. Argument, I think, is what arguments do we want this binary to have, and this defines where the argument should stop. It's something like that. That's why we use documentation, because it says there exactly how this works. But from experience, what we need to call is, oh shit, exec_v bin sh null null. This basically says call bin sh without arguments. This I'm not sure, but I think it says this is it. I want you to call this binary with these arguments and nothing more. This is why the null byte at the end. I'm not sure. Somebody correct me if I'm wrong on this. But what we want to do is this. And we can look in the specifications of which registers hold these values. I think this is, I'm not sure. Is it? I think there are some registers. Is it EDI? Sorry. We use the registers that are meant for this. I have to hurry a bit. It's getting really long. And call exec_v with these values. How we do that? Exactly the same as we did here. We don't have bin sh now at all. Statically compiled binaries does not have bin sh inside because not the whole libc is in the binary. But we can write it somewhere, and we have gets, and we basically write it in some memory address, and then we call exec_v with that pointer. And that's that. It's basically the same problem as this one, just on 32-bit, and it's statically compiled. That's the only difference. Any questions about this? Okay, you can talk to me more about this one on the coffee break. Okay. This one has a lot of code. This one has 150 lines of C, but the vulnerability is like really subtle. And although it has some of the protections disabled, this exploit, it would be a bit harder, but it could also work with everything enabled. I'll talk about how in the demos. So that's it for now. Coffee break, stretch your legs. Yes. Okay, so I hope the coffee was good. Welcome back to the demos. So I have 3 demos prepared. First, we're going to take a look at the PLT and the global offset table in action. I have here compiled just a simple C program, scanf, and it basically says bigger or smaller. And if we use checksec, we can see that everything is enabled, but there is lazy binding, so partial railrow, and we expect that at the beginning of the program, the global offset table will be pointing to the PLT table and PLT table to the global offset table. Basically, it will be a pointer mess. But if we take a look, if we say GDB, break main, run, okay, we go. Okay, so if we say disassemble main, right here we can see that there is a scanf call, and after that two printf calls, and somewhere in between should be a compare. So compare 10. This is the if statement. If scanf read number 10 or higher, print something, otherwise print something else. But if we say info file, we already see the libraries mapped here and everything, but what I'm more interested at is here is a segment called GOT and also PLT. So if we now look at the instruction here, we see that the call instruction is being executed with the argument scanf at PLT. And GDB already resolved the address, and it says this is here. And if we take a look and examine, I'll do Alt-5, examine some instructions here, we see our unconditional jump. We see right here, we have a jump, and GDB also already resolved the address that we are jumping to. And if we take a look where that is, if we examine the pointer there, there's a pointer 45F6. It's here. So what's going on here? This is the PLT table. This address here, if we look at the file, so 5508, 550 here. This is, am I correct? 755028. This is the global offset table. It says got.plt in 32-bit. It's got. It has different names, but this is the got at PLT. And we can see that for now, there's just a pointer back to the PLT. And if we then follow the execution, and we see that there's a push, this push is because legacy. This push is used for the DL resolve binary that we will see in a minute. But what is more important is the unconditional jump that's down here. If we examine the address, oh, that should be instructions to make more sense. For instructions here, we see a push again, and after that, an unconditional jump. Look at where this unconditional jump is going. We can see that there's a libc address, and this is the DL runtime resolve binary. What is happening here? Exactly what we were talking about there. So the scanf, the binary is dynamically linked. Scanf is being called for the first time. In the global offset table, there is no pointer in the libc. So after the jump from PLT to global offset table, the jump for global offset table right back to PLT occurs. And from there, it eventually ends up in DL runtime resolve. And if we now, okay, if we take this address again, examine it, it will say some PLT address. But now I will say next instruction. I will execute the scanf instruction. I'll execute it. I will type, I don't know, 10. Sure. And if we look now at the same address, so if I go back here, we have 55028, 55028, it's a different address here. Before it was 45F6, which pointed back to the PLT table, but now it's something that looks like a libc address. What should be here? What do I expect when I examine this? What should be here? Yes, it's scanf. ISOC 99, let it be. It's scanf. So this is what I wanted you to see in an actual case. It's quite annoying to explain with tables and arrows and graphs because it's quite convoluted. There's a lot of jumps, there's a lot of stuff pointing at each other, and so it's easier to just see it in action. You will need to do this yourself a few times to totally understand what's going on and when does what happen. But with this, you at least have a general understanding of how global offset table works. Remember, this is only in lazy binding. This is only if the binary is compiled with lazy binding. If it's compiled normally, then all of the addresses will already be in the global offset table. No need for resolution, no need for resolving anything. Okay, we've talked about this a lot, so I don't think there are any questions, but are there any questions about the global offset table and the PLT? Okay, in essence, call PLT, PLT jump into global offset table. That's in the essence. Now the fun part. Now we'll take a look at ret to libc. So our newly acquired skill of ret to libc. So we have a simple binary that all it does, a character of 10 bytes, and then reads a lot of data, 200 bytes, and just a random puts after it. So if we run this and put some data in, the program will segfault. If we look at the security, at the protections, file ret to libc, we see that we do not have a canary. Of course, we saw that there was no stack check fail. There's no pi, this is useful, and there's partial rel row. Good. Because we already talked a lot about this technique, I will just show the exploit where that is transferred into code. Basically, we have some definitions here. These are the gadgets. These are all the gadgets that can be found using rob gadget tool or ropper or anything for that measure, or just Control F in hex editor if you like that. But what I want you to pay attention to is this first payload. What does this do? This is the first payload that will get sent after the ROPME string. So right at the beginning of the first gets will read this payload. What does this do? You can trust me that the names of variables are right, and it's actually that in the variables. So at the beginning we have payload equals pad. Pad is short for padding. This is how much garbage we need to write on the stack in order to reach the return address. After that, we have pop RDI return. And after that, global offset table address of puts. We pop RDI, we pop puts at got into RDI. Then we call puts at PLT. When the puts at PLT finishes, we jump back to vuln in order to not crash. In the example on the board, it was all the same, just instead of vuln, there was main. That was the only difference, because there we didn't have vuln. But here we have a vuln function, so we jump back to vuln. Oh, let me just take a look. Okay, so we can just run this and see how it works. It never works on presentations, so it shouldn't, but okay, something is moving. This is always good. Okay. If we disassemble vuln now, we will see that I set a breakpoint right after the gets call, the fgets call, and already on the stack should be our payload. And as we can see, there are a bunch of A's, and after that, some values that look like addresses. And indeed, if we look at this one, this should be which instructions should be on this address? What do I expect to find after executing this examine 3 instructions at here? Based on our payload. So this is the first. This is the value that that overrides the return address. What should be there? Exactly. And we have pop RDI. This is the CSU thingy I was talking about before. They are in every binary basically. Pop RDI. Great. So if we continue the execution, the puts is called. Okay. We have the return instruction, and the return instruction grabs our address from the stack, and we can see that the pop RDI instruction will be executed next. If we look on the stack, here is another address. What does this address represent based on that image again? This will be the address that will be placed in the RDI register. What should be here? This is puts at got. And we can already see that libc address is already here. If we examine this, I hope I'm not with my papers. This is the puts function. Why is the address already here? So this is the global offset table address entry of puts. Why is there a libc address already here? Why do we not need to resolve it? Exactly. So the puts was already called twice, in fact. So the address is already here. And we will load this address into RDI. If we look at RDI up here, we see that the address of puts got loaded into RDI. And now we are executing ret again. And on the stack, there is, I'll ask again, what should this be? So now we've put puts at got into RDI. What do we need to call? Puts PLT. Exactly. And it's exactly what's here. Puts at PLT. Great. So we will now walk through the entire puts, and this should not take long, I trust, I believe. I missed the ret. But as you can see, I've basically flown through the entire puts function, and at the end we've wrapped around and we are back in vuln. Why? Because that's how we set up. And we are back in vuln, and what's different now is that right now we have leaked the address and we already know where every other function in libc is. We do the calculations and we will also print them. I'll just put continue here just to jump at the end of puts again, and I will try to show the standard out. Okay. Oh, something went wrong with the addresses. Oh, this is not right. Okay, let me just. Okay. Okay, something didn't work. Let me just run this one more time quickly. This is the usual presentation stuff that we face. Okay, it worked now. This speaks to the reliability of exploitation that we do. Basically what happened before, immediately the addresses looked weird. They were small, and this does not look like a libc address. This is more like it. So what happened here, if we look at the, no, we're not going to look at the, oh, okay. If we look at the source code, we see that I've put some, yes, this is Python 2, don't judge me, this challenge was a long time ago. If we look here, we see that I've printed out the system and the binsh addresses, and if I now take this address and return back to the debugger and basically say examine string here, it will say that the bin.sh is on this address. And also this all the same if I take this address and go into the debugger and say examine this. No, this is what? This should be this is the puts address. Okay, so I've printed out the puts address that we leaked and also the bin.sh. I don't know what's up with this one. I don't like it. I don't like that very much. I will print some instructions here. It maybe is system. Yeah. Okay, this also does not look very promising. But okay. If we now move on for the second time. Okay, we are jumping into system. I don't know, some weird stuff is going on with printing, but we are actually jumping into system and RDI is set to bin.sh. So what I've just skipped right now, because I was worried that the exploit is not going to work because of some printing errors, I've skipped the other rob chain that builds, that calls system bin.sh. We can see here already. Oh, I can just scroll up. Oh, I can just scroll up. Okay, at the end of the vuln, we had the return instruction, and the return instruction returned into pop string, was put into RDI register. Then we return again, and we jump into system. We can see system test something something, and at the beginning of system, we already have bin.sh in the RDI, and now I can just continue. I'll just let it run. And what happened is the process executed new program bin dash. So basically we've executed a shell. If I kill this and just say quickly, I don't like this line, and run it again, we see that we spawned a shell. It's a working shell. I can do whatever. Okay. Okay, it's not working because on error it crashes. But from here we can spawn working shells. Yeah, I think on error it actually crashes. But it offers remote code execution. If this binary was running on a server somewhere, we'd be able to get remote code execution. Or if this binary would be running somewhere as a SUID binary, we could put some shell code in there, because if we are able to spawn a shell, we are able to put in shell code. A lot of things is possible. This is just a proof of concept spawning a shell. And we can see it's also quite a reliable exploit. It works quite often. So red to libc. We spent, I didn't expect that we are going to actually work through the entire thing on the board. That was really amazing. So we've already covered everything there is to cover about return to libc on the board. Are there any questions about this technique? Is some just little thing that's not clear yet? You can ask me now. It's completely understandable that you understand most of it, but some part is foggy, or some part just seems like, okay, something happens and then we are able to execute bin.sh. You can ask now about that part, because there's no point if you just understand a few basic steps. You'll need a lot of time to piece them together, but I can just tell you now. It'll be easier. So if there are any questions, you can interrupt me at any time, or we can talk later. But now I have a challenge that I've talked before. So this is the one with a lot of code. And I have prepared a normal text editor only for this occasion. No, it's not true. I program a lot in this editor. Okay, so the code is here. Basically, we have a main function, and inside main function there are some basically this was a challenge, so there is some stuff done in the environment to make the exploits as reliable as possible, so you don't need to worry about buffers and virtual buffers and stuff like that, or the process dropping privileges, not being able to print the flag. So these are just some environment setup changes. What's interesting is the vol function, and what the vol function does, it defines an array of 128 bytes and 2 integers. Then it says tell me a story, whatever. It prints, it reads 128 bytes of string, so this is not vulnerable. There is no overflow here because they specified 128 bytes, nothing more. Then we have another printf, and then we read 2 more integers. Then we have an if clause, and the check is called. And if we go higher and look at the check, we'll see that no function is actually called check. We have calculate story score, easy checker, hard checker, but we don't have check nowhere defined. And check is actually a function pointer. It's defined right here. And it points to the hard checker. And what do the hard and easy checker do basically is they are both the same. I think they are exactly the same. There's only one difference. Yeah, this number. So the hard checker expects that the function calculate story score will return a number that is very large, and an easy checker expects that same function to return a score that is rather low, or a number. And if we take a look at the calculate story score, we see that it just takes an array and sums up all the ASCII values of the characters. Basically, it goes byte by byte and says plus equals, plus equals, plus equals. So the return value is just sum of the numbers of the sum of the elements of the array, basically. That's it. And if we go back and look at what is the parameter here, we say the parameter is story, and the story is our story down here. So this is the story. The gist of it is the function that is currently set, hard checker, wants us to give it an array of bytes which sums up to this giant number. But we only have 128 bytes of space. So even if we were able to write all FFs to 125, 225 times 100 still not close, is not nearly enough for this. Did any of you spot the vulnerability yet? Maybe it's subtle. I'll just leave the frame like this. It's in vuln function. It's called vuln for a reason. It should be here. But it's not the vulnerability as you're used to, like giant buffer overflows and stuff. It's just a flaw, a bug in the code. It's what happens a lot, even in big software, in some zero-day vulnerabilities that were found. This is the type of stuff that happens. It's just one check being performed poorly, and so memory gets overwritten. It doesn't need to be all of that memory. It just slightly overwrites memory, and that can already cause mayhem to the system.
Yeah. Negative and no mana.
Yes. So the vulnerability is, yes, buffer underflow is the vulnerability here. So basically, what's the problem here? When we read 2 numbers, the check is if number is less than 10, but this doesn't stop us to write -10 there. And if number is less than 10, then data will be written at an offset negative, I don't know, -3 of the fun pointer. But fun pointer is right above, right under the check pointer. So what we can do here is overwrite the check to point to easy checker instead of hard checker because of a buffer underflow vulnerability. And this is exactly what happens. There should be an exploit here. Yes, it's a simple exploit. There's some extra fluff put on it. This is some Pawn Tools magic that helps us automate exploits easier. It's not relevant for this challenge at all. What is relevant is basically this payload. So we have two addresses. There's no pi. There's no pi. So I should run. Do I have a binary here? Checksec file is equal to 1. So there's no pi, and we know the addresses of hard and easy checker. And here is the payload. These are the two numbers. So -16 and -314. Why these exact values? Because at an offset -16 is the address of hard checker, and if you add -314 to it, it will point to easy checker. This is the logic behind it. Basically the difference between two addresses. The difference between these two addresses is exactly 314. So we say in the payload, add an offset -16, write -314. And if we run this, Python 4, that would be interesting. Yes, we do not need debugger for this. I will just comment this line out. If you run this, we see, yeah, we got end of file, but we can see that my false flag was printed here. Basically, I put in a dummy flag. I put in a dummy flag that says NVT win. This is just a proof of concept. And when I run this, the flag gets printed. Why? Because of this. This basically means that we've passed the check. We can see here that the binary opens a flag file and prints some data out of it. And in this scenario, in this case, it printed my dummy flag. So this is it from the examples today. I thought we were going to spend at least an hour here on the return to libc part, but the power of the board, I guess, worked well in my favor today. So I have nothing more prepared for today, but before I let you go, I want to ask something. Basically, now that we've covered the return to libc, we've basically covered basics of stack exploitation to its fullest extent. The basics. Of course, you can complicate this stuff however you want. You can make this as complicated as exploiting a kernel, or it can be like this. But the point is that I don't want to continue with stack exploitation because stack exploitation is not something that's relevant today. I just wanted to do a few lectures on stack exploitation because it's easiest to get into. You don't need to know as much stuff, and there's not as much preparation needed as for exploiting other vectors in memory corruption. What I would like to do is continue with heap exploitation. Heap exploitation in user space is basically attacking ptmalloc and free. Basically, we'll be learning about use after free vulnerabilities, corrupting malloc returning arbitrary pointers, and one thing that will be very different from what we are doing today is this. If I say checksec file, there's a lot of red and yellow here. When we move on to heap exploitation, there will be nothing red and nothing yellow. So every protection will be enabled, and we will show that it's still not even possible, but it's sometimes easy to exploit, even when every protection is turned on. But for that, we will need to have more lectures. Now, I don't know if we should continue on a bi-weekly basis. The exam season is also nearing, so I don't know how we're going to do that. But I want you to tell me how many of you, just show of hands, would be interested in this series continuing, but on the heap. It will be harder, it will be exhausting, it will be annoying, but there's a lot to teach and a lot to learn on the heap. Okay, so at least 6, 7 people, 8, 9, 10. Okay, I'll round up to 10. And of course, everybody who's watching on the live stream, I don't know how many people are watching, but you're also welcome. Great, this is it for today. You're free to go. Thanks for tuning in. Thanks for battling the stacks with me. Yes, that's it. Bye-bye.